let's say you have this object attached to a spring, and let's say we know the mass of the object, mass m, and let's say we know the spring constant as well, spring constant k, representing how sturdy or how stiff the spring is. And in terms of variables of position, let's say that we keep track of the position of the object with variable x, and some equilibrium position of the spring is x equals 0. So x equals 0 means the spring's at equilibrium. Anything with the spring stretched, like if we move the object to the right, that's the plus x direction. And if we move the spring to the left, compressing the spring, that would be the minus x direction. So x just represents where the object is compared to equilibrium. And if this object is able to move around, what forces would you expect to be acting on the object? What forces could be pushing or pulling on this? Yeah, we've definitely got a force of the spring on the object. And it could be force of friction, or more generally, some sort of, usually we call this the damping force. And this sort of lumps together any force from friction, any force from air resistance or fluid resistance. Maybe this is immersed in water or oil or something. So what we usually call the damping force. So the spring force, damping force, and there might be other forces as well. Maybe there's some other machine attached to this that pushes it every once in a while, or maybe this is attached to something else that it's powering, or maybe this is hung vertically instead of horizontally, and there's a force of gravity as well. So there may be other forces beyond the spring force and the damping force, which we'll just lump together as any other forces, let's say F external. That would add up to the total force on the object. So spring force plus damping force plus any other forces involved. And according to physics, what should all the forces acting on an object add up to? If you add together all the forces acting on an object, that should equal what? 0 if it's not accelerating. But what if it is accelerating? In general, the sum of all the forces on the object add up to, what does a force cause to happen? Like if you push on an object, what happens to it? If you just got some object that's already in motion and you apply a force, what does that do to the object? Not just that the object is moving forwards. Like let's say the object is already moving forwards and you push on it. What happens to the object's motion? Right, it accelerates. The force causes a change to the velocity. And that change might be changing it from not moving to moving. But more generally, the force causes the velocity to change, and we call that acceleration. So the sum of the forces equals, or at least is proportional to acceleration. And what's our multiplier here that links those together? Right, that's the mass of the object. And a very useful way to think of mass is it's the level of difficulty for changing the velocity. The more massive the object is, the more force you need to make it accelerate at a certain rate. So since these are all the forces acting on the object, the spring force, the damping force, and anything else lumped together, those have to add up to mass times acceleration. And we can get some more detail about at least the spring force and the damping force. Spring force, what does the spring force depend on? Like what determines how hard the spring is pushing or pulling on the object? Yeah, both the spring constant and the displacement. Like if the object is at equilibrium, the spring doesn't exert any force at all, which is why we call it equilibrium. If you stretch it a little bit, you get a little bit of force. If you stretch it a lot, then the spring exerts a lot of force. So the spring force is proportional to the displacement, how far you are from equilibrium. And the spring constant is just the constant of proportionality. The spring constant K is what you multiply by the displacement to convert it into a force. So if X is in meters, K will be in newtons per meter. Also, if you stretch the object if you move the object to the right, which direction is the spring force going to be? If the object is on the right side of equilibrium, the spring force is going to be, the displacement is in the positive X direction. But does the spring push you further away from equilibrium or pull you back towards equilibrium? Yeah, the spring is pulling you back towards equilibrium. So if the displacement is positive, the force is in the negative direction. And vice versa. If you compress the spring, you get a force pushing you back towards equilibrium. So if the displacement is negative, then the force is positive. And we can work that into the formula with simply a negative sign. The spring force is negative Kx in the sense that the direction of the force is opposite to the direction of the displacement. And we typically refer to this as a restorative force in the sense that the force is pushing in or pulling in a direction that's trying to restore the equilibrium situation. And in terms of what we saw back in the earlier chapters, would you expect that to lead to stable or unstable equilibrium? Is everything nearby pushing towards or away from that equilibrium? Yeah, everything's pushing towards equilibrium. So this is going to act like stable equilibrium. It's made a little more complicated by the fact that this is not just a first order equation. It's going to turn out to be second order. But we can still say that this equilibrium acts like stable equilibrium because all the forces are pushing towards it. So that's the spring force, negative Kx. What about the damping force? If you got an object moving, what determines how difficult it is to keep moving? What determines how much pushback it gets from the fluid it's in, or the air around it? Like if you're in a car and you hold your hand out the window, you feel the air pushing back on your hand. What determines how hard the air is pushing back on your hand? Not so much the acceleration. The acceleration is the result of all the forces together. But you don't have to be accelerating. You could just be driving along the road with no acceleration at all, and you'd still feel a pushback on your hand from the air if you stick your hand out the window. Right, it's the velocity, not the acceleration. So the faster you're traveling, the more velocity you have, the more pushback you get. Because the faster you're traveling, the more air you have to push out of the way per second in order to move forward. So the damping force ends up being directly proportional to velocity. I think it's more realistic actually to have it be proportional to velocity squared, but proportional to velocity is a pretty close estimate, unless you're going at very fast speeds. And then there's going to be some other constant, which I think we usually refer to as the Greek letter gamma. That's called the damping coefficient, and it represents things like the density of the fluid you're in and also the cross-sectional area. Like the wider the object is, the more fluid it has to push out of the way. So gamma, the damping coefficient, is a combination of the various properties of the system, the cross-sectional area of the object and the density, and I think the viscosity also of the fluid that it's pushing out of the way. Also, is the damping force in the same direction or opposite direction of motion? Is it acting with the motion or against the motion? Right, it's pushing back against. If you're traveling to the north, then the force of damping is pushing back to the south. So we're going to need a negative here as well. Negative gamma V. So that's also kind of a restorative force, not in the sense of position, but in the sense that the force of damping is trying to restore zero velocity. It's trying to return the object to at rest, though not at its initial position. Then the external force, this could be anything. This could be any other force acting on the object. Maybe it's zero, maybe it's a constant, maybe it's dependent on time. But the important thing is the external force is any force that's not proportional to position or proportional to velocity. Essentially, any forces that are proportional to position we're treating as part of the spring. Any forces that are proportional to velocity we're treating as part of damping. Anything that isn't, we're lumping together as the external force. So there's our equation with the formulas filled in. And it's somewhat more convenient if we add these terms to both sides to get F external isolated. So adding Kx to both sides, adding gamma V to both sides, we get mass times acceleration plus damping coefficient times velocity plus spring constant times position equals any external forces other than spring and damping. Any questions on the physics of that so far? And one more or two more substitutions we can make here. What does velocity actually mean? Yeah, it's displacement over time. In other words, it's a derivative. It's the derivative of position with respect to time. So we can replace velocity with derivative of position with respect to time, dx dt. This is where it becomes a differential equation. And likewise, how do we define acceleration? What does acceleration mean as a derivative? Right, acceleration is derivative of velocity with respect to time. But also velocity itself is a derivative. Velocity is the derivative of position with respect to time. So if we're taking the time derivative of a time derivative, what do we call the derivative of a derivative? Right, this is simply the second derivative, d squared over dt squared of x. So velocity is the first derivative of x, position. Acceleration is the second derivative of position. And so this physics equation, just this expansion of Newton's second law, force equals mass times acceleration, if you fill in all the definitions as derivatives, you get a second order differential equation. It's also linear. We just got something times the second derivative plus something times the first derivative plus something times the function equals something. And moreover, those coefficients are all constants. So this becomes a linear constant coefficient second order differential equation, which might be homogeneous or non-homogeneous depending on what the external force is, or rather whether there's an external force or not. And this is why we often call the non-homogeneity the forcing function. The non-homogeneity, the term over here that makes it non-homogeneous, is often called the forcing function because in situations like this, it typically represents some external force applied to the system, some force other than these two predictable ones. So overall, we've got this interaction between the acceleration, which is the second derivative, the velocity, which is the first derivative, the position, which is the function itself, and possibly some other stuff which represent the non-homogeneity in the equation. So any spring situation can be written in this format, as long as you know the mass, the damping coefficient, and the spring constant, and if there's any external forces, then you can write that as a second order differential equation, solve that to figure out a formula for position at any time. And that gives you information about the behavior of the system. Any questions on that so far? And before we get into the forcing function, let's take a look at the behavior without a forcing function. If we have an unforced spring. So if there's no external force, that gives us a homogeneous differential equation. That'll just look like mass times the second derivative plus gamma, the damping coefficient, times the first derivative, plus k, the spring constant, times the function itself, the position. And if there's no external force, those are just going to add up to 0, so we get a homogeneous differential equation. And how would we solve that? What would be our typical guess for a second order linear differential equation with constant coefficients? What would you usually guess for a situation like this? Yeah, we guessed e to the RT. So if we make that guess, that x is e to the something t, e to the RT, we fill that in and its derivatives, and we're going to get a characteristic quadratic. mr squared plus gamma r plus k. And of course, each one of these also has an e to the RT, but we can divide both sides by e to the RT to drop that out. So that's our characteristic quadratic. And then how would you solve that in general? Yeah, anytime you got a, well, I would call this the quadratic, this is a quadratic equation. We can solve it using the quadratic formula. So using the usual quadratic formula, negative b, that'll be negative gamma, plus or minus square root of b squared. So gamma squared minus 4ac will be 4mk, divided by 2a, so that'll be 2 times the mass. So this gives us a general formula for R in terms of the actual physical parameters, the damping coefficient, the spring constant, and the mass that are involved in this situation. And if you have specific numbers, you can fill those in. But in general, I think the important thing to look for here is what kind of solutions do you get? What's the most important part of this formula here in terms of determining what kind of solutions you get here? Yeah, the 4mk, and also what's that interacting with most directly? I would take a look at this gamma squared also. Yeah, because this stuff inside the square root, usually called the discriminant, in the sense that it's discriminating between different kinds of solutions. What sort of values could that be that are going to lead to vastly different results? What could lead to some different results from the square root here? What sort of inputs are going to lead to very different results in a square root? Yeah, negative numbers. And there's really only 3 options for this. This gamma squared minus 4mk, either it's going to be negative, or it's going to be positive, or it could be exactly 0. So we can set up what we usually call a trichotomy. If there's only, in the same sense of dichotomy, but with 3 possibilities instead of just 2. A trichotomy means you've got 3 possible options. And anytime you just got some number, specifically some real number, because gamma, m, and k are all real numbers, gamma squared minus 4mk has to be either 0 or more than 0 or less than 0. So we can split that up into 3 possibilities. This discriminant gamma squared minus 4mk could be greater than 0 or less than 0 or equal to 0. So as long as we can cover each of those 3 possibilities and describe what happens, then we've got all the possible behaviors of this situation. To start with, if gamma squared minus 4mk happens to be positive, what does that tell you about the results of R here? If you take the square root of a positive, what kind of value do you get? Positive, but also we've got plus or minus. So we're adding it and subtracting it. And specifically, would you say that the result is going to be real or imaginary or a complex mix of the two? If you're taking the square root of a positive number, I would expect a real value. And since you're adding and subtracting it, we get two real values. So R is going to be two real numbers. If we get two real numbers for R, and also since gamma, M, and K are all positive, the results are all going to be negative values. So you get two negative real numbers. And going back to our guess in the first place was e to the RT. So that means since we have two of them, we're going to have C1 e to the R1t and C2 e to the R2t. What kind of behavior is that going to be? As long as R1 and R2 are negative real numbers, what would the graphs of these look like? What happens to those as time goes on? As t gets larger and larger, what happens to e to the power of some negative value times t? Yeah, this is going to get closer and closer to zero. These are both going to be exponential decay. So you might get a variety of different approaches, but they're all going to be approaching zero. So this represents a situation where there isn't really any oscillation. A spring isn't bouncing back and forth. You just pull it to some location, maybe give it a shove, and it just grinds towards a halt. It approaches equilibrium and gets slower and slower and just stops there. So situations like this are typically called overdamped. Overdamped in the sense that this happens because the damping is too big compared to M and K. Too much damping means this is a positive result, so you get exponential decay as the behavior. So there's so much damping, so much friction, or such a viscous or heavy fluid that it just grinds to a halt without any oscillation. On the other hand, if gamma squared minus 4mk is less than zero, that is, if gamma is small compared to m and k, so the minus 4mk overwhelms the gamma squared and you get a negative result. If you get a negative value inside the square root, what kind of results do you get? That is, what kind of R values would we get? What happens? Yeah, you get an imaginary number, right? Square root of a negative will be imaginary. And we also have a real part here from the negative gamma. So we end up with a real part plus an imaginary part, and also the same real part minus the same imaginary part. So it's not just any two complex numbers, it's specifically complex conjugates. Complex conjugates meaning same real part, but opposite imaginary part. So we might write that as alpha plus or minus beta I. Same real part, opposite imaginary parts. And note that the real part will be negative because we've got negative gamma over 2m as the real part. So alpha is negative gamma over 2m here. And if you have complex conjugates, we're plugging in complex numbers for R here. What happens when you have e to a complex power? What kind of functions result from that? Yeah, we get sine and cosine. And we also still have an exponential part because if you raise e to the power of alpha plus or minus beta I t, you can split that up with multiplication. You can split it into e to the alpha t times e to the plus or minus beta t I. E to the alpha t, the alpha is a real number. So this is still just an exponential decay function multiplied by e to an imaginary power. E to the pure imaginary power becomes sine and cosine. So we end up with sine and cosine functions multiplied by exponential decay. So that ends up looking like e to the alpha t times C1 cosine beta t plus C2 sine beta t. So we get oscillation, but also exponential decay multiplying it. If that exponential decay wasn't there, if alpha was 0, this would be gone. So we just have oscillation forever. In fact, that's going to happen when gamma is 0, representing an undamped system. So if there's no damping at all, if gamma is 0, then R is going to be pure imaginary numbers. So you get just oscillation forever. It would just keep oscillating the same forever. But with the damping, with the exponential multiplier, what would a multiplier on a cosine or sine usually affect? Like, let's say it was a constant multiplier. If you just got a sine function and you multiply by 5, what would that times 5 do to the sine function? It's not going to increase the phase. It doesn't change how much time it takes for one cycle. That would be if you modified what's inside the cosine function. Like if you had cosine of 5t and you change it to cosine of 10t, that would change how much time it takes for one full cycle. But a multiplier outside the cosine or sine function, how is that going to stretch it? What would that affect most directly? Yeah, that's going to affect the amplitude. A multiplier inside the function is most directly affecting t, so it stretches and compresses in the t direction. But a multiplier outside the function is most directly affecting the resulting y value, so it stretches or compresses in the y direction. This multiplier changes the amplitude. But since it's not a constant multiplier, it's a changing multiplier as time passes. That means we get a changing amplitude. So what's going to happen here is instead of having a sine function with a constant amplitude, we get an amplitude that exponentially decays. So we start with a large amplitude, and then it shrinks towards 0 from both sides. So the amplitude is getting smaller, and we're going to end up with a sine function or cosine function or combination of those that looks kind of like this. It's a decaying oscillator. The amount of time for one full cycle stays the same, and that amount of time is typically called the quasi-period. Quasi-period because it's not truly a period because it's not truly a cyclic function. It's not repeating the same cycle over and over again. It's just repeating similar cycles that get smaller and smaller. So we call this a quasi-period in terms of the amount of time it takes to repeat the similar cycle. But it is repeating similar cycles in terms of proportional to each other. They're just getting smaller and smaller as we go further and further down the line. So this would be a decaying oscillator. It is able to oscillate. There's not enough damping as there was before. There's not as much damping as there was before. Previously, when we had two real solutions, that was because there was so much damping, it couldn't oscillate at all. It just grinds to a halt at equilibrium. Now we're talking about less damping. Less damping, not enough damping to stop it from oscillating, means it does oscillate. But if there's even any damping at all, the oscillations are going to gradually slow down in the sense of getting smaller and smaller. We're losing energy due to damping, so that means the oscillations get weaker. Still takes the same amount of time to complete one oscillation, but the size of the oscillations is getting smaller. So that would be a decaying oscillator, and we would call this an underdamped situation in the sense that there's not enough damping to overwhelm the mass in the spring constant. So an underdamped situation leads to decaying oscillations. Any questions on those cases so far? So that covers what happens if there's too much damping, if there's not enough damping, possibly even including no damping at all. Then you just get an undamped oscillator that continues sinusoidally forever. And last we have if this gamma squared minus 4mk equals exactly 0. And that is pretty rare in the sense that that only happens if gamma happens to be exactly enough that gamma squared equals 4mk. Not just that you've got more damping or less damping, but if you've got exactly the right amount of damping. If gamma squared is exactly 4mk, then the discriminant is going to be exactly 0. If that whole square root becomes 0, what does that tell you about the solutions to the quadratic? What kind of solutions do you get and how many solutions? Yeah, you get identical solutions, a repeated root. Because if this gamma squared minus 4mk is 0, you get negative gamma plus 0 and negative gamma minus 0. Those are the same. So that means instead of getting 2 real numbers or 2 complex numbers, you just get 1 real number, negative gamma over 2m. It is real, so that means we do still get e to the RT. It's still exponential function, but there's only one of them. So we're going to have to deal with that repeated root. So one of the solutions is still e to the RT, r being negative gamma over 2m. So that is negative, so we do get exponential decay, but we need a second solution. If you got a repeated root, one of the solutions is e to the RT. What's the other solution? What would y2 have to look like? What's your typical second solution in a repeated root case? Yeah, that's going to be t e to the RT. And there are various ways you could get that. Reduction of order is one, or using the Wronskian and Abel's theorem. But in general, if e to the RT is a solution because you had only one r value, in that repeated root case, the other solution is always going to be t e to the RT. So we end up with kind of exponential decay, but also a modifier with this times t. Everything's still going to approach 0. It's still going to approach the axis as an asymptote. But it's this t modifies how it approaches it. It's kind of difficult to distinguish visually. It ends up kind of looking like it goes through sort of a partial oscillation, but then approaches 0 without any further oscillation. So it's just going to cross the axis once at most, and then just approach 0. Because there's just barely enough damping to prevent oscillation. Any less damping and you get oscillation. But this much damping or more and you get no oscillation at all. And since this is an edge case, this is just barely enough damping to prevent oscillation. We typically call this critically damped. Critical in the sense of a critical point. That it's just barely the edge case. Any less damping and you get oscillation. Any more damping and you don't. So those are really the only 3 possibilities. Either there's not enough damping, so you get oscillations, or there's too much damping, so you get no oscillations at all. It just grinds to a halt at equilibrium. Or you're on the edge. You have just barely enough damping to prevent oscillation. So that would be critically damped. And for any no external force spring mass system, these are the only possibilities. Any questions on that trichotomy there? And generally this means as long as you've got the mass and the damping coefficient and the spring constant, you can run this analysis very quickly. You don't even need to solve the differential equation. If all you care about is this going to oscillate or not, check gamma squared minus 4mk. If that's positive, then you get exponential decay, no oscillations at all. If this is negative, then you do get oscillations, but as long as there is damping at all, then it's going to be decaying oscillations. Oscillations getting smaller and smaller as time passes. Whereas if gamma squared minus 4mk is exactly 0, that's critically damped. So it doesn't oscillate, but any less damping and it will oscillate. It's just barely enough to prevent oscillations. Any other questions on these spring systems? All right, then let's try a quick example where there is an external force. let's say we have a mass and a damping coefficient and a spring constant. Let's say those are, what was I going to use for that? Let's say mass 1 kilogram, spring constant 5, and damping coefficient 4. And I'm going to leave off the units here, but let's assume that they all match up, newtons per meter, and I think that would be newton seconds per meter. And let's say those add up to an external force of, let's say 5t squared. That is, we've got a force that starts off at nothing, because when t is 0, this is 0. But an externally applied force that gradually gets stronger and stronger as time passes, proportional to how much time has passed squared. In that case, how would you solve a non-homogeneous differential equation like this? How would you start that? Yeah, we'd start by guessing e to the RT again. Because in general, to solve a non-homogeneous differential equation, we start by pretending it's homogeneous. Assume we're dealing with the corresponding homogeneous equation, and we solve that by the usual methods. We guess e to the RT, fill that in, and find the characteristic quadratic. And then we can solve that by factoring, if possible, or quadratic formula in general. Before we even do, though, if you actually calculate gamma squared minus 4mk, gamma is 4, so we get 16. 4 times 1 times 5. -4. What does that suggest? If the discriminant is negative, what happens when we're going to take the square root, though? Yeah, this is actually going to be underdamped, because when we take the square root of gamma squared minus 4mk, square root of -4 is going to be imaginary. That means we get complex values for r, specifically a complex conjugate pair, and that's going to lead to oscillations, sinusoidal oscillations, with an exponential decay modifier, because we do have some damping. So let's see what that's going to be. R would be negative gamma plus or minus square root of the discriminant, which we already calculated, so we can just fill that in, over 2 times that first number, 2 times 1. So that'll be -4 plus or minus square root of -4 would be 2i all over 2. So -2 plus or minus I. That would be the R values here. And when we fill those into our guess, we would have C1 e to the -2 plus IT and C2 e to the -2 minus IT. If we expand that with Euler's formula and simplify, what sort of functions would you expect this to turn into? What happens when you raise e to an imaginary power? Because note that we can factor in e to the -2t out of both of these. Each one of these can be written as e to the -2t times e to the it or e to the -it. Yeah, we factor out the e to the -2t, and what's left is going to be sine and cosine functions. Specifically, we should end up with just C1 cosine of the imaginary coefficient, which is 1t, and likewise C2 times sine of the imaginary coefficient, which is still 1t. So this should be our homogeneous general solution. I'm going to write x sub h here because it's the homogeneous solution. E to the -2t, that makes it a decaying oscillator. times this combination of sine and cosine, C1 cosine t plus C2 sine t. Any questions on that so far? So that's our homogeneous solution. What do we need to do to turn that into the non-homogeneous solution, the solution to the actual differential equation we have here? Yeah, we're going to need any one particular solution of the non-homogeneous equation. So we'll take our homogeneous solution, our homogeneous general solution, and add any one particular solution, xp, that makes this equation true. Because if you fill in the homogeneous solution, this whole thing turns into 0. We want something that turns into 5t squared instead. So we're going to need plus one other thing that turns into 5t squared. The particular solution makes it turn into 5t squared. Adding the homogeneous solution doesn't change that because x sub h just turns into 0 when you fill it in here. But introducing the C1 and C2 allows it to cover all solutions instead of just one. To find that particular solution, I think in this case, because 5t squared is a fairly straightforward function, I would use the undetermined coefficients method. Undetermined coefficients is we're going to make a guess that the particular solution is based on the 5t squared here. What guess would you make for the particular solution? We've got something t squared. So I would start by just guessing something t squared. The problem is, if we want to check that, we'd have to fill it in for x and x prime and x double prime. So we need to check the derivative and second derivative. What's the derivative of at squared? Yeah, 2at. And the thing is, that's a new type of function. If our guess is a quadratic, just t squared, but our derivative has a t in it, we'd have a t squared term and a t term that doesn't cancel out. So we're going to need to include a t term in our guess also. So let's say plus bt. That way the t term in the function and the t term in the derivative have at least a chance of canceling out and leaving exactly 5t squared. But what's the derivative of bt? Because we've got to include that in our derivative of our guess now. Yeah, specifically 1b. That's a constant, which means that our derivative is going to have a constant and we don't have anything to cancel out the constant because we don't want to have plus a constant over here. So what we need to do is include plus a constant in our guess also. Generally, I would recommend making a guess based on what the non-homogeneity looks like. Take the derivative. If that derivative introduces a new type of function, include that new type of function in your guess as well. And keep going until, what's the derivative of plus c? Yeah, plus 0. That doesn't introduce a new type of function, so we can stop here. The fact that t squared eventually becomes 0 when you take enough derivatives is the reason why the undetermined coefficients method works, because we don't have to keep going forever. We eventually get to a stopping point. So this should work as our guess. There's our derivative of our guess. And then of course, we'll need the second derivative, which will just be 2a. So we can now fill these into the original differential equation. X double prime plus 4 times x prime plus 5 times our guess has to equal 5t squared. And this looks like just one equation, but you can actually split it up into 3 equations, because once you simplify this, what you'll end up with some amount of t squared, some coefficient, including probably a's, b's, and c's times t squared. That coefficient has to equal 5. You'll also get some coefficient times t, but we have no plus t on this side, so the coefficient of t has to be 0. You'll probably also get plus some constant that doesn't depend on t, but does depend on a, b, and c. That constant has to equal 0 because there's no plus a constant on this side. So this actually turns into 3 equations, and we have 3 unknowns, a, b, and c. So you can solve that system of equations, find values for a, b, and c, fill those in here, and that's your x particular that you can add to the homogeneous solution. Homogeneous solution, including unknown C1 and C2, plus particular solution after you find values of A, B, and C is the general solution of the actual differential equation. At that point, if you have initial conditions, you could also fill in the initial conditions and solve for C1 and C2 in the actual final result here, not in the homogeneous solution alone. Any other questions on that? All right, so give that a try, and we will take a look at some more examples next time.